All right, now that we've gotten our first example out of the way and kind of you have more of a feeling for how this method works, let's go back and fill in that one sentence of why we group like terms together. And I told you it's because we want our equation to be true for all x. So basically what we're doing is we're saying that we want the solution to work no matter what x value is plugged in. So we need equations that don't depend on x. And the way we do that is by grouping by like terms that are functions of x. And as you see more examples, hopefully that becomes a bit more concrete. The other thing we're going to do is we're going to talk about the second way that we choose our G1, G2, so on and so forth. And so our first one was that we just use terms that appear in G of x, and we saw an example like that. The second consideration we're going to have is that we might need to use derivatives of terms in G of x. So for example, if we had that y double prime minus y prime minus 1, anything on the left, oh, well, that should have been y anyhow. Y equal to, instead of 2x squared plus 3x plus 4, let's just say it was only 2x squared. Then we would still say, okay, G1 is probably x squared. But we're still going to say that G2 could be x and G3 could be 1. And the G2 equal x, G3 equal 1 come from the idea that anything we see in our G of x, we should also include all of its possible derivatives. If you forget to do this, you won't cover all the potential solutions and your y sub p might be incomplete. So we're going to do an example that shows this. Let's see, something with sines and cosines would be good. Here we go. So now we're going to try to solve y double prime minus y prime plus y equal to 2 sine 3x. And to solve this problem, sort of first what you would do is you would solve the homogeneous case y double prime minus y prime plus y equal to 0 using methods from last class. And I'm just going to tell you right now that if you went through that process, what you would get is that y1 is equal to e to the 1/2 x cosine of root 3 over 2x, and y2 equal to 1/2, e to the 1/2 x sine of root 3 over 2x. So you could do that using methods from last class, and we're not going to do that here because it's not a good use of your time, since you already know how to do it. So then our g of x, using the notation for this section, is just that part on the right-hand side, 2 sine 3x. And now what we want to do is build our y sub p. And so using our first principle, we would say, okay, sine 3x appears in my g of x, so I think that that is in my y sub p. And if you do that, you won't have enough in y in order to find the particular solution. So you also have to follow our second principle where you say, well, sine 3x has a derivative, it's cosine 3x, so I'd better include that too. So kind of, this was from part A, and this is from part B, little a, little b. And then once you've done this, you've built the shape of y sub p that works for this problem. So let's just make a note to ourselves. Remember, we need derivatives of all g of x. And so in this case, the derivative of sine is cosine. All right, so now that we have y sub p, our goal is to plug it into the differential equation. That means we're going to have to take derivatives of it. So let's go ahead and do that now. y sub p prime is going to be 3a cosine 3x minus 3b sine 3x. And then yp double prime, since this is a second order equation, I'm going to need that as well, is going to be 9 times a sine 3x, and that's going to give me a negative sign again. And then minus 9 times b cosine 3x. And what we're going to do is we're going to try to plug this into our differential equation. So we want y sub p double prime minus y sub p prime plus y sub p to satisfy the differential equation. So I want that to be equal to 2 sine 3x. And let's see how we do. Okay, so this is going to be too much for this space. So I'm going to go ahead and start plugging it in right here on this next slide, because I'm just going to have to copy it over again anyhow. So my y sub p double prime was minus 9a sine 3x minus 9b cosine 3x. And then it's minus y prime, so minus 3a cosine 3x minus 3b sine 3x plus y. So plus a sine 3x plus b cosine 3x. And I want that to be all equal to 2 sine 3x. So hopefully you can kind of already see why I needed to include cosine in my y sub p, because if I had only had sine, then cosine would have shown up in my middle derivative, but not in my final derivative. And so when I did the group-like terms, I could group all my sines together, but that one cosine would be all by itself, and I would have an equation I couldn't possibly solve. But now I have cosines and sines all over, and I want to group everything together. So the two things that look like my y sub p, my g1, g2, are going to be my sine terms and my cosine terms. So let's do the sine terms first. I'll do red. So there's minus 9a times sine minus 3b times sine plus a on the left-hand side. And so that's going to give me minus 9 plus 3b plus, minus 9a right there, plus a. And then I want my cosine 3x terms. And we'll do green, I guess. So I've got my minus 9b right there, minus 3a plus b. So that's going to give me minus 9b minus 3a plus b. And on the right-hand side, I've got sine 3x times 2. And I've got a cosine 3x. It's just times 0. So there's no term there. And let's go ahead and pause here and continue the example in the next video, because the other one ran over and I don't want to do that to y'all again.